as promised, now we're going to start computing some examples. So we're going to compute some class groups and write down what they look like, as groups and so on. So let's start with a very simple example. So computing class groups. Example. I'll give the name of this example 4.1.1. So you'll see that this isn't very hard. So I'm going to let I be the usual square root of -1. So we're going to look at the class group of the Gaussian integers. Let's look at k being the q of I, this Gaussian field, and want to compute the class group of k. So how do we start? First thing we need to do is calculate the Minkowski bound, and I'm gonna copy it over this definition. No, that's not what I want to do. I'm gonna copy over the definition of the Minkowski bound so that we can just plug in the numbers. First, we compute the Minkowski bound, and mk, which is equal to this thing. Make it a little bit smaller. Voila. So remember, n was a degree of I field, R2 is a number of complex conjugate pairs of embeddings, and this is the square root of the discriminant. So I need to figure out all of these things. So here, this is a degree 2 field. The degree of k to q, this is imaginary quadratic, so this is 2. So which is by definition what n is. So n is 2. So n equals 2. This is an imaginary quadratic field. So in this case, R2 equals 1. Where we just take, there's 2 embeddings and they're complex conjugate to each other. So we only count up the pairs. So we have this, and R2 is 1, as this is imaginary quadratic field. So we need to figure out what the discriminant is. What is the discriminant of OK? Well, we've done this before for quadratic fields. I told you exactly how to compute the discriminant, or we did this in examples. So we've seen how to do this. For quadratic fields. Fields, and here we get, and it was just some condition on like what the residue, if it's 1 mod 4 or 2 or 3 mod 4. In this case, it's -1 mod 4. So, and we get, in this case, the discriminant of OK is just -4. Great. So let's figure out what the Minkowski bound. So the Minkowski bound of this is, it says 2 factorial over 2 squared times 4 over pi to the 1, because R2 is 1, times the square root of the absolute value of the discriminant, so it's square root of the absolute value of -4. So this is 2 factorial over, well, let's figure this, so this is 2 over pi times the square root of 4, which, this is 4 over pi, which is something like, you just need to know approximately what this looks like, 1.273 or something. So all we need to, we know that every ideal contains some class of less than the Minkowski bound. So somehow we need a rough estimate, the closest integer to this Minkowski bound. What does this tell us? Well, if you go back to, so note that theorem 4.0.3 then tells us that, so the normal ideal is always an integer. So every class in the class group contains an ideal of norm less than 1.2. So in particular, it has to contain a class of norm less than equal to 1. So this one tells us that each class in a CLK contains an ideal of norm less than or equal to 1.273, i.e. I'm going to forget it tells us it contains an ideal at norm less than 1. Ignore the fractional part. But the only ideal of norm 1 is the trivial ideal. There's only one ideal of norm less than or equal to 1, and it's a trivial one. I.e. just the ideal generated by 1. So every class contains this class that I said 1. In particular, the class group has to be trivial. CLK is trivial, which what we said last time means that this is in fact a PID, which means that in fact that this thing is a UFD. So it follows that K is a PID and therefore also a UFD. Great. Let's do another. This was a very trivial example. Here there was almost nothing to calculate because once we've done the Minkowski bound, basically there was nothing. The Minkowski bound was too small to give us anything useful, to give us any non-trivial classes showing up. So here's two more interesting examples. So example 4.1.3. I'm gonna let's take k to be q the square root of minus 5. This should be a bit more exciting. We know what the ring of integers in here is by the theorem 2.1.11. We know. So we know here that OK is z square root minus 5. Again, we gotta figure out the R1s and R2s because we want to figure out the Minkowski bound. R1 is 0, R2 is 1. The number of real embeddings is 0. This is an imaginary product. The imaginary complex and conjugate embeddings is 1. And the discriminant of this case, in this phase, the discriminant of this field is, you'll work out, in this case it's minus 20. So there was an exercise in the notes which you should do, which was to figure out what the discriminants are for quadratic fields. So this is just plug in the numbers to a formula and we get this. Or you can just work it out by hand. Therefore, what do we get? You'll see why I calculated the ring of integers in a minute, because we'll actually need to factor some ideals. Therefore, we have, what do we have? What's our Minkowski bound? The Minkowski bound is the degree of our field, so it's 2 factorial over 2 squared again, times 4 over pi to the 1 times the square root of 20. Just the square root of the absolute value of the discriminant, which, okay, you can write this down as just like the square root of 8 pi times the square root of 80 or something, which, whatever it is, I know it's less than 3. So this means, sorry, I got this wrong. This should be something like, okay, well, I don't remember exactly what the thing was, but I know that in total this number that you get here is less than 3. Okay, so this means every class contains an ideal of norm at least 1, or less than 3, so norm 1 and 2. This means every class in the class group contains an ideal of norm 1 or 2. It has to be the Minkowski bound is strictly less than 3. So this contains an ideal of norm 1 or 2. We know that there's only the trivial ideal of norm 1, so we got to figure out what are the ideals of norm 2. So we need to figure out the ideals of norm 2. How do we do this? So we've done this before. I have a reference here that we did this in the proof of corollary 3.4.10. So as we saw in the proof of corollary 3.4.10, it's enough to look at prime ideals dividing 2. Dividing the ideal generated by 2. And we know how to factor ideals in quadratic fields. We have a theorem that tells us this. By theorem, just go and look it up. 3.5.17, we can do this without even having to think. The ideal 2 factors as the follows. The factor is 2 comma 1 plus square root of minus 5 squared. I'll call this P2 squared. Where P2, this means that there's only one ideal showing up in the factorization of 2, and P2 is a prime ideal of norm. In this case, you can see that it's norm 2. The ramification degree is 2, so that means that the residue in a quadratic field, that means that the residue degree is 1, and the norm of this ideal is p to the residue degree, so it's 2 to the 1, so it's 2. Okay, so there is only one prime ideal of norm 2. So what does this mean? So this means that the class group has either 1 or 2 elements. It's either we have the class group of K is just the trivial element, or the class group of K obviously has the identity and it has this ideal of norm 2, where this only happens if we don't know at the moment if these two classes of these ideals are the same. So this is an ideal. This is a prime ideal of norm 2. I know that this ideal isn't the trivial ideal because it's a prime ideal. That's fine. But what I don't know is I don't know in the class group if it gives me a non-trivial class. Like, for all I know, I could take this ideal by 2. I could multiply it by some other principal ideal, and then suddenly it becomes principal. That's what would mean for this ideal to be trivial. So, if they weren't the same. So, my theorem, the theorem that I have 4.0.3 tells me, well, the classes are going to be represented by elements of norm, in this case, 1 or 2. There's only one thing of norm 1. So I find how many ideals of norm 2 there are. You do this by factoring the number, the prime ideal 2. So the prime number 2 in this ideal into the thing. We can just read off the theorem what it is. It tells us that there is only one prime ideal of norm 2. So every class contains an ideal of norm 1 or 2. There's only 2 choices for this thing. So either a class is trivial, or it's the whole thing, or it's this group of order 2. So we need to figure out if the class of this ideal P2 is trivial or not. So we need to check if this thing equals 1 or not. How do we do this? Well, as I said before, checking that if this was the case, then this would mean that P2 is principal. So if this ideal was if this class was a trivial class, this would mean what would this mean? To mean P2 is principal. You can check that if you have an ideal such that when you multiply this by some other principal ideal, it becomes principal, then the ideal that you started with had to be principal. This was an exercise in the notes somewhere. So if this class was trivial, then P2 would have to be principal, which by this proposition, we know what the norms of principal ideals look like. So proposition 3.4.5 would mean, what would it mean? So if P2, this would mean that P2 is something like x plus y square root of minus 5. It would be principal, and because we know that it has norm 2, this would mean, this proposition is telling us that the norm of this element, the absolute value of the norm of this element, would have to be 2. This is what this proposition is saying. Obviously, x and y here are just some elements of z. Okay, so this absolute value of this norm would have to be 2, i.e. the norm has to be plus or minus 2. Great. So can we have any elements of norm 2 is the question that we need to answer. So does OK have any elements of norm plus or minus 2? That's the question I want to answer. What's the norm of a general element here? So what's the norm of some random element like this? So the norm K to Q, if you work this out, you know how to do this. You'll figure out, we did this in an example for quadratics, so you don't even need to think about it. This is x squared plus 5 y squared. And this, if you just consider if this is equal to, can this be plus or minus 2, then it can't be just like reduce mod 4 or look at it as something mod 2. Does OK have an element of norm 2? i.e. does this can this thing equal plus or minus 2? Answer no. Just I don't know. The usual case is reduce. Here we go. I'm sure if you just reduce mod 4, you get the answer. X and y are integers, so just reduce this thing mod 4, and you figure out that you can't have the sum of two squares being 2 mod 4, or minus 2 mod 4, or maybe it's just reduce mod 2. Maybe it's not reduce mod 4. All right, I'm gonna let you think about why this is the case. Answer no. Yeah, the answer is no. Yeah, it's easy, because in this case you don't reduce mod 4. It doesn't work for x is 0 or 1 and y is 0 or 1. Once you plug in a number bigger than 0 or 1 for x and y, then this number is always bigger than 2, so it doesn't work. No, since this number is greater than 2 for x and y greater than 1. And for 0, 1, it doesn't work, obviously. So you can't have this. So the class of P2 can't be can't be the trivial class, because there can't be any elements of norm 2. Therefore, the class group of K is this denoted by 2 elements, 2, and is isomorphic. So what's the only group of size 2? It's isomorphic to C2. Great. So that's our second example. Here's the first example was a trivial class group. Here we had a class of size 2. I'll do one more example. Maybe something a bit more involved. Let's do a number field degree 3 or something. So there's more examples in the notes. I'm skipping one from the notes, but you can go back and look. So 4.1.5. Let's do this one. I'm going to take K to be some cubic field. So it's going to be Q cube root of 7. Let alpha be the cube root of 7. So this isn't because this isn't the quadratic field. We don't have all the results already written for us for quadratics, like what the discriminant is. Well, we can figure out what the discriminant is, but we don't have like what the ring of integers is, and so on. So we have to do a little bit of thinking here. But here clearly the minimal polynomial is x cubed minus 7. Obviously this is monic, and this is Eisenstein p equals 7. The minimal polynomial is this, and the discriminant. So once I know what the minimal polynomial is, I can figure out what the discriminant of the following basis of 1 alpha squared. This discriminant, if you work it out, what is it? It's minus 3 cubed times 7 squared. So now, what do we need to do? I need to find the discriminant of my number field, which means I need to figure out what the basis is for my ring of integers. So I need to do this. So I've taken my minimal polynomial. I have my discriminant. It's 3 cubed times 7 squared. This is irreducible by Eisenstein at 7, so I wouldn't have to worry about 7, but I do have to worry about 3. But let's do the usual trick of like changing variables to make this work. So note that if I take f of x to be x plus 7 cubed minus 7, then f of x is it's going to be reducible. It's going to be Eisenstein at p equals 3 and p equals 7 at the same time. So if beta is a root of f of x, we have, what do we have? The roots are just like one's a linear combination of the other. So we have q of beta is isomorphic to q of alpha, the root, well, remember alpha was just the cube root of 7. We know O of the ring of integers now of q of beta, because we don't have to, it's Eisenstein at the two places that we care about, so we know that OK is Z adjoin beta, which is the same thing because they're just linear. There's just a shift by 7 on my root. This is just the alpha. So my alpha was a basis. So OK in this case is, well, let me just rewrite what alpha is, the third root of 7. So this is what my my ring of integers is. So we can now, well, this is actually the discriminant of my field, 3 cubed times 3 squared. And moreover, notice that because my OK is the full ring of integers, my ring of integers is Z adjoin alpha. This theorem, which allowed me to factor, which was telling me how to factor ideals generated by primes in the thing. Remember that there was this condition about the prime not dividing some index. In this case, it means because of the two things are the same, it works for every prime, so I don't have to worry about anything. So we have all of this. So OK is that, and the discriminant of OK, now we know it's minus 3 cubed times 7 squared. Similarly, what do we need for the Minkowski bound? R1 in this case is going to be 1. There's going to be one real embedding, and there's going to be 2 complex conjugate embeddings. So it's going to be one pair of complex conjugate embeddings. So putting this together, we get what do we get? We get the Minkowski bound of K is, in this case, it's a degree 3 field, so it's 3 factorial over 3 cubed times 4 over pi to the R1 times the square root of 3 cubed times 7 squared. That's the value of this. So if you work out what this is about, this is roughly 10.3. Great. This is one of the reasons why in live exams people are allowed calculators, is so they can calculate the Minkowski bound. Or sometimes you just tell, you just get given the Minkowski bound. Okay, so in this case we need to find all ideals up to norm 10. So we need to find all ideals of norm up to 10. Great. So we look at the primes less than 10 and we factor these in things. So let's factor 2, 3, 5, and 7 using, I don't know this theorem that we have, but there's this Forest theorem 3.5.10, which I'm just going to note that, which has OK is the same thing as Z alpha works for all primes. Great. So let's factor these ideals. Remember, what does this mean? Well, we've done this. Now we have to just factorize the minimal polynomial mod p. So take the minimal polynomial, which we and factor it mod 2, 3, 5, and 7. So let's do this. So we have like x cubed minus 7. This is congruent to x minus 1, x squared plus x plus 1 mod 2. What is this mod 3? This is x minus 1 cubed mod 3. X cubed minus 7. This is x minus 3. So I've done this before. You can. It's not that there's a super quick way of doing this, which I'm not telling you. I've already done this example, and I'm just writing out what the answers are. So you get this mod 5 and mod 7. Well, this is easy. This is congruent to x cubed mod 7. Notice that this makes sense. We talked about what primes ramify. We said that if a prime ramifies, then it has to have divide a discriminant. So here 3 ramifies, and notice that 3 divides a discriminant, and 7 ramifies, and then 7 divides a discriminant. In any case, once I've factored my my ideals, I immediately get what the factorization. Sorry, once I factor my polynomial, I get what the factorization of my ideals are. So from this, what do we get? We get the following. So the ideal generated by 2 factors as what I'm going to call P2 dashed. This is 2, 1 minus alpha, 2 alpha squared plus alpha plus 1. This is what these ideals are. 3, this factors as P cubed, P3 cubed. Oh, sorry, did I? Oh, I made a typo in the notes. It's P3 cubed, and this is just 3 minus alpha minus 1 cubed. 5. What do we get? We get P5 primed, which is 5 and alpha minus 3, and then I have 5 alpha squared plus 3 alpha minus 1. And lastly, the ideal generated by 7. Again, this is ramified. This is on P7 cubed, which is just 7 and alpha cubed, which is just the ideal generated by 7. Sorry, the ideal generated by alpha cubed. Notice that alpha cubed is 7. So these two ideals are actually the same. In any case, not only do we get the factorization of the ideals, we get their norms. Here we get that the norm of P2 is 2, and the norm of P2 primed is 2 squared. Remember, it's 2 to the residue degree, which is 2 to the degree of the polynomial showing up here. So this is 2 to the 1, because it's like a degree 1 polynomial alpha, and 2 to the 2 is a degree 2 polynomial alpha. Similarly, we get the norm of P3 is 3. The norm of P5, the first one is 5, and the other one is 5 squared. And lastly, the norm of P7 is 7. Great. So here I now have my list. Ooh, nothing on that. I now have I've factored all the ideals of prime showing up in the primes less than 10. So I now know what all the ideals. Well, this is all the ideals of norm less than 10 are going to be built up from these ideals. So what ideals? If I combine these, what are the ideals I can construct of norm less than 10? So okay, do we need to rule out some? So here first, for example, P5 dash, this has norm 5 squared, so this is bigger than 10, so I can ignore it. All I really need to consider are these ideals. Here, this set of ideals, these are all the ones that show up. So we have it. So every ideal of norm less than 10 is formed by products. So you have your P2, P2 primed, P3, P5, and P7. So all of the ideas are formed like this. So we somehow just need to understand the group structure for it. This is like a set of generators now for my group, and it's got to understand if they're distinct or not in the class group. So that's for the ideals. And the next question is, are these ideals distinct in the class group? Question mark. So there's some that we can do easily. I've just seen, for example, that P7 cubed is so P7 is just the ideal generated by alpha, so this already is trivial. So clearly, yeah, the class of P7 is the trivial one, as P7 is just the ideal generated by alpha, which is principal. And for example, we know that these two ideals multiply to 2, so the product of these two ideals is the principal ideal. So as classes, this tells me that the elements are inverse. So this is similar for the other ones. Since, for example, 2 is ideal P2 times P2 dashed, we get that whatever the class of P2 is going to be the inverse of this class. So I'll put this just like this. So we have this sort of equality. If you take classes of, put square brackets on all of this, this tells you, this equality tells you that this is P2 primed. So just, this is a group, move it to the other side, you get this equality there. Maybe I'll just copy this. Just saying, as this. Okay, so and well, P5 and P5 prime are also going to be inverses, but we don't have to worry about P5 prime because it has, the norm is too big, so we just don't worry about that. But also notice that this means that you can have an ideal whose inverse has a different norm in the class group. Oh, I took the 2 away with it. Okay, so we know there's 2 things, but we need to figure out if any of the other ideals are principled or not. So, are any of these, first of all, are these distinct in the class? Well, let's maybe just do the first, an easier question. Are these ideals non-trivial, first of all? So the first, this one I showed, it's trivial. I don't know if this one is trivial, but I know what that P2 and what its inverse is. But I'm not sure if either is trivial, and I'm not sure about the P3 and P2 and P5. So I gotta ask myself, are these ideals trivial? What does it mean to be trivial in the class group? It means that it will be principal. If it was principal, then that would mean that there's some element of norm, and say like 2, 4. Yeah, this would tell me that if P2 was principal, then tell me there's an element of norm 2. If P2 prime was principal, then tell me that's an element of norm 4. So then tell me that's an element of norm 3, 5, and 7, for example. Well, we don't know this is trivial. We know that's an element of norm 7, which is just alpha. So let's look at the norm of the elements. Let's look at what the possible norms of elements are. So let's look at the norms of elements in okay. So here's something that you can work out by hand if you want. So the norm of a general element x plus y alpha plus z alpha squared. You can write this as x cubed plus 7y cubed plus 49 z cubed minus 21x y z. As I said before, sometimes for like specific fields, there's easy formulas. For cubics, I think you can maybe work, maybe you should try to do this next time. You can probably work out a general formula for what the norm of a cubic is, if you know what the generating thing is. If it's a sufficiently nice generating one. In this case, you work out that this is what the norm of a general element is. And the question about these being non-trivial in the class group is asking, can this number be 2, 4, or something like this? So, do we have elements of norm, what was it, 2, well, it's not norm 2, if P2 was trivial, then P2 inverse would have to be trivial, so I don't have to worry about P2. So do we have any elements of norm 2, 3, or 5? How do we see this? So we need to figure out if this equation can be equal to 2, 3, or to plus or minus 2, plus or minus 3, plus or minus 5. So in this case, it's somehow you just reduce mod 7. So looking mod 7, we see that the norm of a general element notice that here I'm just using that 7. Yes, notice that 7 is dividing 7.9 and 21. Notice that the norm of a general element is a cube mod 7. 7, right? If I reduce mod 7, then I just get x cubed. And is 2, 3, or 5 a cube mod 7? No. So as the only cubes, seven are plus or minus 1. See that there are no elements of norm 2, 3, and 5. Great. So the class of these ideals, the class of ideal 2, the class of ideal 3, the class of ideal 5 are not trivial. So at the moment, and notice that P2 primed is it's just the inverse of the class of P2, so I don't have to worry about that at the moment. So at the moment, I have at least 4 generators for my group. So, oops, where did that come from? Go away. The class group of K has at most 4 elements. What are the well, we have either the identity, and then we have either could have these things here, but we don't know if these elements are distinct. For all we know, two of these ideals could generate the same class in the class group, i.e. they could differ by a principal ideal. There could be a multiple principal ideal. So we need to figure this out. So are these elements distinct? So okay, we know that they're not these three elements aren't one because I just checked the non-trivial, but are these elements between themselves distinct? So we've got to think about this. This is maybe maybe the slightly tricky bit, or the thing where you have to somehow start realizing what. Once you see an example done, hopefully you'll see what to do in general. So the first thing to note is, for example, the ideal P3. We know that when we cube it, it becomes the ideal 3. So whatever the P3 is, it's going to have order in the class group 3, because when it's cubed, it becomes a principal ideal. So the first thing to note is that since P3 cubed is the ideal denoted by 3, we have that this element has has order 3 in the class group. It's doesn't have order 1 because we checked it's not trivial, so it does have an order 3. So this group does contain an element of order 3. And here's a trick. So somehow to figure out if these two things, if any of these two things are the same, then you maybe want to look for elements of norm. So this has norm 2, this has norm 3, this has norm 5. You maybe want to look for elements of your ring which have norm like 6 or 15 or something like this. So to see if, for example, P2 is different than P3, or P3 is different from P5, and so on. So we look at elements of a small norm. So in this case, maybe it's cheating, but here's what I'm trying to get to this. So note that if you think about you might notice that the norm of the following element, 2 plus the cube root of 7, so 2 plus alpha, this has norm 15, and here's another element, norm cube of minus 1 plus cube root of 7, this has norm 6. Therefore, since we only have one ideal of norm 3, and one ideal of norms 2, 3, and 5, you can immediately factor the ideals that these elements generate. What do you get? You can get 2 plus cube root of 7. This ideal that this thing generates has to be P3 times P5, and the other one, this has to be P2 times P3. So in particular, if I multiply these two ideals, I get a principal ideal. In particular, these two things are inverses in the class group. Therefore, as class ideals in the class group, P3 times P, or P5 times P3 is trivial, and the class of P2, class of P3 is also trivial. So what do we get? We get P3. Let me write this two together. I get the class of P5 the same as the class of P3 inverse, which again on this, if you look on the other side, is the same as the class of P2. So these two ideals give me the same class, and it's the class of P3 inverse. Therefore, CLK, the class group is generated by this 3 and has size 3. So therefore, and thus has size 3. So it's just a cyclic group of order 3. So it's C3, and if we can give its multiplication table. I didn't do this for the other example because we're a bit trivial, but think of the multiplication table of this thing. So here's my ideals. Spread this out a bit. That's like, so if you just do the multiplication table, so here you get 1 times. Well, so basically the multiplication for P3. P3 squared, P3 squared. What do I get if I do P3 times P3? Well, I get the class of P3 squared. If I get P3 times P3 squared, I know that P3 cubed is 1, so I just get 1 here, and then here I get P3. So this is what my class group looks like. It's a cycle group of C size 3, and this is what the multiplication table for my elements are. Great. So this is the end of the examples. If you look at the notes, there's another example, as well as like a description of the algorithm, how to do this. It's just the steps which I've taken, like find the ring of the steps that I've just done here, for example, which was find the minimal polynomial in the ring of integers. So, well, find a discriminant. So for that, I need to find the ring of integers. So I did this usual trick. We know how to find a ring of integers. Once I know what the discriminant is of my field, I need the ring of integers I gotta find what the ring of integers is to find the discriminants of the field. Once I found this, I found my Minkowski bound. I then have to factor all ideals up to my Minkowski bound, all the prime ideals up to my, so all the ideals generated by prime numbers up to my Minkowski bound. So it's this. We know how to do this. You're just reducing minimal polynomial mod p. Do all of this. This is what the factorizations are, and immediately tells you what the norms are. So I figure out all the norms are of these ideals and just take the ones which are less than 10. Any element of norm less than 10 is going to be generated by products of these things in this example. So, if you have an element of an ideal of norm 6, it's going to be, P2 times P3, because this is the only way to get these sorts of things. And so then I have some candidates for my things in my class group, and somehow I have to figure out, are these elements trivial, and are there any relationships between them? So are they trivial? Well, somehow just looking at the factorizations allows you to see some of them are trivial. So P7 was trivial. You also get some like relationships between them. P2 and P2 primes have to be inverse to each other. The class group. Being trivial means that you're principal. So if you're principal, then that would mean that there exists an element of norm, whatever the prime was. So in this case, it's an element of norm 2, 3, or 5. Some horrible computation because now we're doing cubics. Can you have elements of norm 2, 3, or 5? We figured out we couldn't. So these elements aren't trivial. Is there anything next is, are there any relationships between them, between these elements? And by looking at elements of small norm, you can somehow try and figure out, here I found an element of norm 15 and 6. This somehow gives me a relationship between P3 and P5, and P2 and P3. And that was enough to figure out what the class group was. So in general, it can be, you can imagine how this can get very complicated. Yeah, this is the end of examples for class groups, and then the last thing is I'm going to do is show you how to use these class groups and so on to figure out solutions to some Diophantine equations. That'll be next time.